we are discussing how to steal from a busy processor without too much fuss for the busy processor. Okay, and the algorithm is essentially at the base level. You simply figure out a new end for the busy processor and write it. Okay, and then you in private copy the remaining elements and do something with it. Okay, so issue is that the end that you wrote, the other processor, the busy processor may have gone past that end by the time you wrote it, because the other processor doesn't know that you are trying to steal so far. Okay.
And cannot be cached as well.
So there should be some
Cached.
Yeah, you may have cached end, right?
So let's again not talk about cache issues. Anytime you are sharing things, cache is always going to play spoil sport. So you have to turn it into a volatile type thing. And that's a given, right? If you are sharing a resource, make sure that it's volatile. Yeah, you had
there
a.
should be some conditional check before updating that end. Okay, already that end has passed on, so only one should be stealing from that particular.
So that is one option. Right? You can say, I was too slow updating the end. How would I know? I have to reread the front.
First, before updating, I need to one read basically where the end lies of that particular business, and then I can update it. Because
If I read before I update, that does not help, because after that, when I update, that by that time it may have proceeded, right? So I have to update and then read. Okay. So I've updated the end. Then I read where the front has reached, maybe beyond. If the front is before end, then I know that that guy is going to stop at the new end. If the front has passed end, then what are the possible things we can do?
It won't go further.
I update this end to the current front and start stealing from the current front.
I can continue, I can say now my steal failed and re-steal. Right?
Just take this new front, forget your front.
I mean, this person will not. Right.
Actually, that will work. If you take the new front,
But it will stop. You start from there. You don't have to
Start
redo what
stealing
he
from
already
the
started.
you instead of starting from end plus 1, start from front plus 1. Will it work?
Yes, sir.
But you need to take the new angles.
New end, your end is their old end, so that doesn't change. And if their front is beyond their old end, then your front is beyond your new old end, and so you will not do anything more.
So, but both the processors need to realize this, that that the end has changed at the same time, right?
Not necessarily.
And what if you read the front and the other process, the BG process, is still doing work and it goes beyond the front, and then or it won't go actually.
It won't go beyond the end,
Since
but
it-
there is a race condition on front. If you recall, I haven't shown you the parallel version yet, but it's where is it? Never mind. Yeah, this. So you are saying front plus plus. The stealer, does it see the front before the plus plus or after the plus plus? So it's a matter of one job. So if you're okay by having one job overlap, then maybe it's okay. If you leave at this point, you can guarantee that at most one job will be done by both the busy processor and the idle processor. Okay. Alternatively, you can simply make this increment atomic. Okay. So the next thing I wanted to talk about are how to do this on a linked list. So I have lots of different processors, shared linked list, and I want to edit. And for the time being, we'll say all the edits are happening through this interface that we provide. You can find elements in a linked list, or you can add a new node, you can delete. That's the only thing you can do. Okay. So let's talk about insertion. I give you a pointer, cursor, into the linked list and say insert after this. That's the typical way in which you would insert. So one way is you create a new node. Okay, this new node has its own reference, some n. You fill this new node with the value you want to add into the linked list. You make its next pointer to be the cursor. Cursor 0 is where we are inserting after cursor 0. You make its next pointer to be cursor 0.next. Right. So far, the original list is as it was. Now I am going to atomically switch. What am I going to switch? Cursor 0.next is equal to n. Assuming that is it's not always the case, depending on what your underlying architecture is. But let's say a variable assignment of whatever size, or let's say a pointer assignment, is atomic. Okay. It may not be in reality, but for the time being, let's assume. So we simply say cursor 0.next is equal to n.
For example, if two are trying to insert, only one would be set and I'll use the.
Right. So one will be lost. So both of them started off. Both of them said cursor 0, created a new node. Both of them made that new node point to cursor 1, right? And now they are atomically trying to set cursor 0.next to their new node. One of them will succeed, one of them will fail, and that insertion will have got lost. Okay.
No, you can do the cast, right?
If you were not doing cast. If you're doing cast, then what do you do? What should the cast do?
Check whether the updated, what it returned was the old.
So it knows what is the old cursor 0.next. That's the thing it's trying to modify, and it will only modify it if cursor 0.next was still cursor 1. Okay. So we can now do this in a cast sense. What if that fails? You try, right? Because basically the node structure has changed. Two people want to insert after this node. It's not clear whether I should go first or that guy should go first. Somebody has to coordinate. So whoever happened to succeed is as if that operation succeeded, and somebody has to figure out where this new thing should go, after that other new thing or before that other new thing. So you just redo it. What if concurrent cursor 1 meantime was deleted? So if you did, this is the cast that you would have done, but it would still not work if cursor 1 has gone away. So how do you fix that? Let's see what deletion should do.
You don't free it.
Sorry?
You don't free that thing, you just mark it.
We just mark what?
Set a boolean to true that it has been deleted, but not free the list.
Is it in the list? Freeing is one issue, right? In Java, you don't even free.
But the pointer will still change, right? Keep the pointer just mark it.
Yeah, just mark it. Right.
So you have to mark, if you mark it, right? Deletions don't actually happen. They're only marked deletions. Then this doesn't happen, right? That the thing you are pointing to has gone away. It is still there. But anybody proceeding through the list has to skip past this marked deletions. And this kind of defeats the purpose, right? You never delete a node now. All your deleted nodes are only marked. And at some point, you will have lots of this junk lying between any two valid nodes. So we would like to delete it. But marking is a good suggestion. and in fact, there's this algorithm actually uses that. So let's see how deletion might work. We are deleting the thing at cursor 1. For us to delete, we have to know the pointer, the reference to the previous node, because that node's pointer is going to go past it, right? So this is going to go away, and that's going to happen. But if there is concurrent insert and delete, then we know bad things happen. Right? So simply doing this pointer assignment using a CAS is not going to be sufficient. So what we are looking for is two CASes, right? We have a node, there's a node on this side that is pointing to it, there's a node on this side that it is pointing to. We want to make sure that that hasn't changed and that hasn't changed at the same time. So there are richer variants of CAS that some systems support. Most don't. So you can't simply say, do this as long as that variable is this and this variable is that. So we have to do something else, and that something else will be applying a mark, just like we just discussed. Okay, so there was an insertion happening and things will go bad. So how will this mark business work? This is work by Tim Harris from 2001. You do mark, but you have to garbage clean. You have to get rid of the things that you have marked. Mark is only temporary to go across the fact that nobody is doing two things at the same time. Okay. So how will this work? Ultimately, you have to get rid of the marked things. If you never had to get rid of the marked things, then you're done.
Basically, when you ensure that no one is operating on that internet.
No insert on the remove the
That means you're saying that at some point you lock the entire list, nobody else works on it, and remove garbage clean. That's how actually garbage cleaning typically works. They have this macro locks that lock out everything, at least for a small period of time. That's not a great solution.
inserting fourth or
While inserting it, just we check there is some marks, so we have inserted the things.
That will of course be true, right? Whenever there is mark, you'll never be inserting after the mark, right? Because typically insertion is after a search. You search for a location and then you say insert over here.
Yes, but the problem was when we were inserting by chance that would be related simultaneously. And this insertion. While inserting the things in parallel, put a check over there that there is things marks. Lock and
We have to put some kind of lock,
some kind of lock
right?
is needed.
Because if we simply say don't do this if it is unmarked,
But
then just as after you have checked whether it is unmarked, somebody will have marked it. Right? So there is a race on mark also. And so it may seem that you have simply postponed the decision. When you are actually going to delete it, something may go wrong. But actually, basically it works the same way as you just said. You keep opportunistically removing these dead nodes using CAS still. So search, insert or delete, whichever finds a dead node, removes it. Okay.
what's wrong with inserting the fourth node after the second node?
Inserting the fourth node being the last node after the second node. You delete it and then insert it again. What do you mean?
No, so I delete the third node, that's like marking it, and that is immediately followed by insert the fourth node after the second.
But in the meantime, this green node has come along. Right, so same problem remains. You don't want the black node.
See, two concurrent insertions.
No, two concurrent may also happen. So multiple such green nodes may happen. But right now we're talking about while you were deleting the red node, a green node was inserted. So if after having deleted the green node, you say now take my node and insert it after this other black node, when did you get this other black node? If you got it before, then you're pointing to the wrong black node. Then the green is the one that you have to be inserting. Okay, so this is going to work by simply marking it first, right? Just this way. You make a mark, and the best way to do this is simply use some bits of the pointer, at least in a theoretical sense, and also make it into a struct where there's a mark and a pointer so that it goes together. Here we are using one of the bits of the pointer. So when I talk about reference of this entity, then I'm talking about taking the pointer out. When I'm talking about mark, I'm taking the mark out. Okay, it's in the same place. So I say cursor1 dot next. As long as it remains next, I'm not just going to blindly mark. It still has to follow the thing I was expecting it to be pointing to. Then I make it marked. Okay, and what you see here is looks like next I mark, but it's really next ORed with mark. So both next and mark are being written over there. Or next combined with mark, or is not necessarily the only way. And after you do this, somebody may come along and do whatever they want. It's perfectly fine. They just have to realize that marked nodes are to be skipped over, and so they shouldn't be inserting after the mark node. And now you yourself try to remove the mark. So as long as the marked node still is in that position, right? Previous is pointing to the marked node. Nobody has done an insertion just before it. You can go ahead and delete the mark. Right? You can go back and write just the pointer part of it, the unmarked pointer. What can go wrong? See, the first case, if it doesn't succeed, then you know deletion didn't happen. Right? Somebody else was messing up with that area at that time. So you have to figure out where to delete next. Now deletion has happened, but the other thing didn't succeed. You couldn't remove the mark.
What are we doing in the and then?
I'll show you. Basically, and then says that you first do the mark and then try to remove the mark. Okay. But it's possible that when you try to remove the mark, you fail because somebody else was in that area doing something. Because I want to remove the marked node. Yeah. So if you see, its previous.next is going to point to next. Okay. As long as it still is pointing to a marked node. So nobody has come along to do anything better. Okay. And so now I'll show you what I mean by and then. It goes something like this. Somehow you have a method of figuring out where the current and previous should be. Right? So for example, when I'm inserting, I fail, I say update my current, previous and current. I delete, in deletion I fail, I say update my previous and current, so that I can make sure that I know where I should be deleting from or where I should be inserting to. So think of update as is the context sensitive method that knows how to tell me where the insertion or deletion should be happening.
Need the first statement to be a cache?
What do you think?
I'm just marking it, so I don't care what if my next step. Just marking it to delete.
Is that enough? What if somebody else was trying to do something there? Somebody else might be trying to delete it.
Yeah,
So then
Somebody else may be trying to insert something just before it, and so you're after that insertion, you say, I've pointed over here, I have this element that lies between here and the next, this dot next needs to go, and somebody else has modified this pointer to somebody else, and because it has inserted. Now if you mark it here, you may be marking the wrong node.
Pointed to the node, right?
Yes.
This one now.
No, I'm assuming here that when you have just inserted something before it, this may not be the node you want to delete, right?
I search for some value from this value here and I want to. I'm not saying that I want to delete the next node next to this node. So this node is part of it.
Let me finish this session and continue this discussion. So let's get back to where we were. We're talking about marking a node that has been deleted, and we're just talking about why does this need to be cast. Okay, and it is checking that the node that you are deleting is still pointing to the node that you were expecting after it, right? But that by itself seems innocuous, right? Or seems like it's not needed. But remember that when you write a mark, you're writing a pointer that you have read before, modified with the flag, with the mark. Right? So in this scheme of things, pointer and the mark go together. So you've read a pointer to the next, and now you're saying write the marked thing, marked pointer, same pointer but marked. If in the meantime somebody has inserted something, then the pointer you're writing is stale. Right? So you couldn't be writing the same pointer. So it's not simply saying turn this bit on.
If you chose it to implement it that way.
If you chose to implement it that way, that complication will show up somewhere. With when you have it one item protected by CAS, you'll now have to have two items protected by CAS in the second one. Right? So it's going to show up somewhere. Okay. So you have a method that figures out where the pointers should be. You have a method which checks if the reference has that bit turned on. Right? For any reference, you can say whether it's a marked reference or an unmarked reference, and so it checks if it is not a marked entry. Then you're going to do that CAS thing. CAS is a marked version. So when you see mark the current pointer, so that function mark is adding that bit, the next bar pointer from the previous line. Otherwise, your CAS failed. Here are seeing the Boolean variant of CAS. So you go back, update your pointers and delete again. Right? So you go to the end of the loop and go back to the true part. If you succeeded, then you break out of the loop. That means you were able to figure out where you have to delete from. You're able to write a marked reference to the next thing over there, and you've come out. Now you simply try to CAS the mark out, and if you succeed, good. If you didn't, again something else has gone wrong. It is possible to continuously do this loop until you do succeed. It is suggested, for example, by the authors of this paper, is to build it into the underlying semantics of the list, where you say that if you are seeing a marked reference, then you skip it in the find and in the insert, but you delete it there. So instead of repeating it right now, you opportunistically repeat it. Anytime you see a marked thing, you try to delete it, and then skip over it. If you don't see a mark, then it's like a regular list. Okay. But this is what it would do in general. You keep going forward until you keep seeing a marked reference, right? Because now you can have multiple of these marked references, one after the other. Okay, that's as much as we were going to talk about for examples of lock-free synchronization. Are there any questions on that?
Here also can we maintain with each pointer a value, like in the previous example we did for each processor, we were trying to say whether it has been acquired by some other processor or not. So if we just maintain a value with each pointer, and whoever is going to modify a node, it will lock 2 pointers, then nobody else.
But then that's lots of locks, right?
With each node there will be 1 lock.
Exactly. So you've got to, if there is a variable, so it's not really for a node, it's for the connection of 2 nodes, right? And so every connection, you've got a variable that you have to cast. And you have to say, I can edit that link, or I cannot edit that link. And so there's lots of extra variables that you have to deal with in that case. Okay. I'm going to quickly go through some of the things that I was going to talk about. This is one that I was not going to talk about, but since it was brought up, here is one slide for out of course sorting. Okay. In fact, Nitesh isn't here today. You have n elements to sort. Okay, and this is the most basic, right? This is essentially a variant of the algorithm given in the Knuth's Art of Programming volumes. So you have m items you can store in the memory at one time, n items to sort. Okay, and this is merge based. So you take n things at a time. M things at a time, because only that much will fit in your memory, and sort each chunk. So now at the end of it, you have m blocks of m things each sorted, right? But n over m of them, and you have to merge them together. One method is you figure out how many such things are, right? M over m ceiling, S such things are there, and you make a small buffer, depending on how big this value S is. The buffer is m over s plus 1, right? Meaning that you divide your memory, available memory, into s plus 1 chunks. Each chunk will get B items. So now you have enough space to read B items from each of these blocks you had created. So now you're going to do a merge across all of them. Right? So you have so many blocks, some items from every block. You only have to look at the first, and the smallest of the first items is going to go in the result block, and that result block is why s plus 1 is there. Right? S things for the input, one more thing for the output. When the output block gets saturated, you have filled it, you put it into a file, right? You output it and empty that block out and continue. When one of the input blocks gets emptied, because all of its elements have gone into the saturated or into the output block, you refill it. You go to that particular chunk and read. What are the problems? There are problems that you may see. First of all, before we talk about problems, How many times is each data item read? From the disk, yes. So here the main thing you're worried about is how many blocks you're reading from the disk rather than the number of CPU operations. Although that will also play a role. Right? Typically these blocks will be big enough and you want to do efficient internal sorting. But for the time being we are not worrying about that. Twice, right? In the beginning when you read it, you sorted it and wrote it. Read once, written once. Again, the next time you read in its appropriate block, appropriate stream, if you will, and write once. Read once, write once. Okay, so twice read and twice written. Okay, what are the...
You take double the space of it's nothing 1 terabyte, you need 2 terabyte because after it's sorted, you can't remove the.
What do you mean you'll use to? You're only using M elements of main memory.
So I'm just talking about the input. Input, you're going to start and you're going to create a new file for output.
That can also be optimized, but yes, the basic that is one problem. That
Double the disk space.
your disk space doubles, although typically disk space is not what you worry about these days.
Your output block gets filled much faster than the input blocks will need to be fetched. So maybe first, like, let's say if it's uniformly distributed data, then you only be reading one element from each of the S blocks and your output block will get increasing the size of the output block, like maybe.
So there's no need for the output block to be the same size as the input blocks. Yes, that's a good point.
Maybe assuming that all the sorted blocks can come at a time.
So in the beginning, you're reading all of them. Right? So you're waiting for all the reads to happen before you can start the merge. Because the first element of everything has to be read before you can start the merge. And potentially there's a lot of such streams that you're generating. So and at the other end of the extreme, you may be 2. You just read 2, the smaller of the 2 you write out. But it may not be the grand smallest. So then you have to merge by pairs, and now you're reading and writing it more than twice. And typically there will be a trade-off. Okay, so you'll say, don't read only 2 at a time and merge them, but maybe read a large number of them, merge them, read another large number of them, merge them, and then a few more passes of this. So now instead of reading it twice, you're reading it a few times and merging them. And again, parallel I/O is another issue that we are not thinking about, but all of these processors are reading at the same time, and you have to worry about where these different blocks are stored. Okay, so that is one thing. The other thing I wanted to remind you, if nothing else, that there are very simple problems, run-of-the-mill daily problems, which are not parallelizing. Which means that anytime you see a sequential variant where you have to do depth first search, you have to think about a new algorithm, non-depth first search based algorithm, and so on and so forth. Right? So how would depth first search be slow? It's very sequential, right? You go from one node to the next, you can come back or go further. What would be a kind of parallel variant? You'll be exploring from many places, essentially, right? But then you have to worry about when the two start to meet. Okay. So the algorithm changes in flavor significantly. Let me show you one where it is not quite a depth first search, but has that favor, but more importantly, just a pure parallelization. And I'm not going to go into details of a more expensive, more optimized, less expensive algorithm, which do exist, but a basic straightforward parallelization. This is the Prim's minimum spanning tree algorithm. How does this work? You grow the minimum spanning tree, right? You start at any arbitrary vertex and you say the minimum cost edge coming out of this vertex has to be in the minimum spanning tree, and you bring it into the MST, and you say let's look at all the edges going out of MST. The smallest of those has to be in the MST. Let's bring it in. It's a very sequential process, right? And so it's not a great algorithm for parallelization, but if you were to parallelize it, how would we?
Randomly put
You can do nothing about this fact that you have to grow one at a time. So you will say let's at least parallelize the growing, right? How much time it takes to grow can be speeded up, and so a parallel version of Prim's algorithm would simply repeat this n times, and what will it repeat n times? It will say, so again I'm assuming here that there are p processors, n nodes, and each node is going to be responsible for n over p of, and each processor is going to be responsible for n over p of the nodes, okay? And it's going to ask, is any of my node connected to MST? If it is connected to MST, what is its cost? It's going to find the minimum of all its nodes going into SF, the edges of its nodes going into MST. It's going to find the min, then you do a reduction to find the grand minimum, right, the global minimum, and that node becomes the next node to be added when you are done with this iteration. Okay. If it's shared memory, then you write that after reduction, that everybody knows what the reduced value is, and they update the MST, they add that node to their local view of the MST and repeat. Okay. How long would that take? So order n is the outer iteration. What about the inside? Basically, it's what your share of nodes is, right? For every node, you're going to ask the question, how many things it is connected to in the MST.
I'm having it. My nodes are upgrade the number of processors to my units. But at certain level, if graph has enough number of nodes.
The MST has enough number of nodes.
And for each of these nodes, I need to check the next stage to be connected. At that stage, my n is greater than p, then only efficiently that parallelization should go.
No, even in the beginning, right? In the beginning, what you're saying is I've got all these nodes, and I don't know how many of them are connected to the MST. So I'm going to figure out, right? Then we are going to go the other way and see which one of them, and you can do it in a more optimized way also. This is kind of the brute force.
Finding the maximum spanning tree looks to be a parallel.
Maximum spanning tree?
Yeah.
The minimum spanning tree is also.
Yeah, same. They're the same thing.
Yeah.
So is it not as simple as starting from each vertex and going to tree and then the tree merge?
No. Right? Because you still have to first of all, you have to figure out how to partition the graph. Once you have partitioned the graph.
So the graph is very big enough. Some processors are like find the processors randomly grow trees essentially.
It's not just the processors, but their edges also have to be partitioned. Which edges am I considering in my MST and which edges go across?
Since the MST is unique.
No, for example, suppose we said we are starting at two places, right? And we simply follow this. Everybody says take your minima. Doesn't work. You're going to get something else. You're not going to get MST.
But we shoot it in the sense we arbitrarily choose any vertex and then start with it. Right? That way it is.
But there are problems that are going to happen when you are going to come and you have no way of knowing which you should take. There is no straightforward parallel version of it.
Suppose initially working with less number of processes and I start with just one vertex and do the mean finding as a reduction. So straight away you reduce from ordering mean finding to long mean finding.
Sorry?
So you start with just one process. Suppose you have some P process, start with one process, find the first edge, starting with some vertex, right? And then you gradually increase the number of processes, like as we do in breeding trees. In that way, when we are doing mean finding to go the MST by one edge, so that mean finding which was sequential earlier.
No, min finding is not sequential.
No, earlier it was sequential. Suppose when we build the sequential, the MST sequential, now it has become log n time reduction.
The log p time.
Log p time.
Right, but there is n by p work that has to be done. There's n by p that you have to find the minimum across, and so that has to be included. So it's going to be n by p times n plus log of p times n. Okay. All right. I want to stop here. There's nothing I can begin now that is going to end in time.